How are you today? Today we are going to discuss on the reactions of alcohols with hydrochloric acid. Earlier on, we had discussed about reactions of alcohols with hydrobromic acid, but today we are going to start on a different reaction, that is of alcohols with hydrochloric acid towards the synthesis of alkyl chlorides. So this is a general reaction where you have the alcohol reacting with hydrochloric acid in the presence of water and zinc chloride to form an alkyl chloride. Hydrochloric acid reacts with alcohols in much the same way that hydrobromic acid does. For example, concentrated aqueous HCl reacts with tert-butyl alcohol to give tert-butyl chloride. So this is an example. It's a specific example where you have tert-butyl alcohol. This compound is a tert-butyl alcohol because the carbon which is bearing the hydroxyl group is tertiary. It's bonded to 3 other carbon atoms, and it's butyl because there is a total number of 4 carbon atoms. So that's why it's known as tert-butyl alcohol. That's a common name. And then when you react that compound, that alcohol with HCl in the presence of water, then you'll be able to get or synthesize tert-butyl chloride in very good yields. And you can see the yield in this case is 98%. So that is very good yield plus water. So water is usually the leaving group. When you have alcohols reacting with hydrohalic acids, not necessarily only hydrochloric acid, you also have maybe hydrobromic acid or any hydrohalic acids, then you always get water as a leaving group. So they always water when any hydrohalic acid reacts with an alcohol towards the synthesis of any alkyl halide. There's always water, which is a leaving group. Chloride ions is a weaker nucleophile as compared to the bromide ions, as we saw the reaction between alcohols and hydrobromic acid. So when you compare the chloride in hydrochloric acid and also the bromide in hydrobromic acid, the chloride ions is a weaker nucleophile as compared to the bromide ion because it's smaller and less polarizable. We will discuss what polarizability means in later lectures. So therefore, an addition of Lewis acid, that is an electron acceptor, such as zinc chloride, is sometimes necessary to promote the reaction of hydrochloric acid with primary and secondary alcohols. And that is mainly because the chloride ion is a bit weaker as compared to the bromide ion. So zinc chloride coordinates with oxygen of the alcohol in the same way as a proton does, except that the zinc chloride coordinates even more strongly. So the reagent, which is composed of hydrochloric acid and zinc chloride, is usually known as the Lucas reagent. And secondary and tertiary alcohols react with this reagent, that's the Lucas reagent, by the SN1 mechanisms, while the methyl alcohols and primary alcohols react with the Lucas reagent via SN2 mechanism. We will discuss what those two mechanisms entails. So this is an SN1 mechanism, and SN1 reactions with Lucas reagents are usually fast reactions, and usually the substrate or the alcohol which needs to react with the zinc chloride in the presence of HCl is usually either secondary alcohol or tertiary alcohol. And another thing you need to note is that SN1 reactions always proceed via formation of a carbocation, or there's always ionization through the SN1 mechanism. So you'll see there will be a carbocation which will be formed in one of the steps. Then finally, the chloride ion donates electrons towards stabilizing that positive charge on the carbon atom. So this is the first step. The first step, as we've already, as I've already indicated, is a coordination of with the zinc chloride. So the lone pair of electrons of oxygen in the hydroxyl group of the alcohol will coordinate with zinc chloride, and then it forms this transition state, or it forms this intermediate. So again, as I had indicated earlier, is that when a lone pair of electron is used to form a bond with electron-lacking species, there is always a positive charge on the atom, which is donating a lone pair of electrons towards the formation of a covalent bond. So in this case, this lone pair of electron has been used to form this covalent bond to zinc. And remember, zinc chloride initially in this particular step is neutral, but now it is having a negative charge, and it's because of the introduction of the 2 electrons of this covalent bond. That's why there's a negative charge on zinc. Then there's a positive charge. Again, we've said it's because of the use of the lone pair of electrons on oxygen to form a new covalent bond with zinc. So the next step, so one of the reasons, one of the consequences of coordinating with zinc chloride is number one, to make the hydroxyl group a better leaving group, because as I had indicated in earlier lectures, hydroxyl group is a very poor leaving group. And also I indicated that leaving groups, good leaving groups, are usually relatively stable. Even if they leave with a charge, they should always be relatively stable, like the halide ions. And that's why you find that when you have alkyl halides as substrate for synthesis of a number of other reagents, then it's usually a better substrate as compared to alcohols, because it has halogens. Halides are very good leaving group because they are relatively stable as compared to the hydroxide ion. So hydroxide ion, once it leaves, it's usually very unstable and therefore has to react with an electron lacking species so that it can get neutralized. So that's why it's a very poor leaving group. So the first step for all alcohols to react as good substrates for nucleophilic substitution reactions is that they have the OH group has to be converted to a beta leaving group. So the coordination with zinc chloride is just towards achieving that property of making the hydroxyl group a beta leaving group. That's number one. Number two, when the oxygen coordinates with zinc chloride, it also makes this electrophilic carbon more electrophilic, or the electrophilicity of this carbon, which is bonded to the oxygen, will be improved with the coordination with zinc chloride so that it can easily react with any nucleophile. So those are the two the consequences of coordination of the OH with zinc chloride. It makes this bond even more polar. It is already polar, but because of the bond between carbon and oxygen being more electronegative, will make the oxygen have some partial negative charge and carbon some partial positive charge. And when an atom has some partial positive charge or complete positive charge, then it's usually electrophilic, that is electron lacking. But if it has a negative charge, either partial negative charge and also complete negative charge, then it's also nucleophilic and donate electrons. So the bond is already polarized, but coordinating it with zinc chloride makes it even more polar, and it also makes this carbon more electrophilic, and it also makes the hydroxyl group a better leaving group. So it now can easily undergo nucleophilic substitution reactions to result to another product. So you can start from an alcohol, react with the appropriate reagents, and synthesize a number of other products. And in this case, you are starting with an alcohol. This is a secondary alcohol, reacting it with the zinc chloride, and then also in the presence of HCl, and then you result to the synthesis of an alkyl chloride. So this is one of the ways in which alkyl chlorides can be synthesized from alcohols. So let's go back again. So here, this bond has now been highly polarized. And then another consequence of coordinating the hydroxyl group with zinc chloride is that it's going to result to this positive charge. And because of this positive charge, this bond will be highly polarized. And this covalent bond to carbon and oxygen will tend to break, and the 2 electrons will tend to stabilize that positive charge. And when the substrate or the starting alcohol is a secondary or tertiary alcohol, then what will happen is that this is going to break and 2 electrons will be used, or they will flow towards neutralizing this positive charge and result to a carbocation formation. So this is a secondary carbocation from a secondary alcohol. Or you can also have a tertiary alcohol resulting to a tertiary carbocations. So tertiary and secondary carbocations can easily form But if you have primary alcohols and also methyl alcohols reacting with the same reagents or the Lucas reagents, the reaction does not proceed via formation of this carbocation. There will be no step where you'll see carbon bearing a positive charge. You'll see, I will explain later. So this is SN1, an example of SN1. There's always the reaction proceeding via carbocation formation. So there will be one step where you see carbon bearing a positive charge, which will be formed. And why when you're starting with secondary or tertiary alcohols, you can easily form at secondary or tertiary carbocations because those two are stable. When we were discussing when we are arranging or when we are rating the stability of carbocations, you realize in the earlier lecture that we indicated, or I indicated, that tertiary carbocations are the most stable, followed by secondary carbocations, followed by the primary carbocations. Then the least unstable are the methyl carbocations. So the methyl carbocations and primary carbocations hardly form, but the secondary and tertiary, because they are relatively stable more than those other two, can easily form. So this is a secondary carbocation and it's relatively stable. And why is it relatively stable? Because it's flagged by two alkyl groups, in this case, two methyl groups. And usually alkyl groups always stabilize the positive charge or reduce the level of that positive charge towards stability. Stability is when you don't have any charge. So they will reduce this positive charge through it is usually through hyperconjugation. We will also discuss about that later. So secondary carbocation has two alkyl groups which can easily donate electrons or stabilize this positive charge. So it can be stabilized by this alkyl group, also these other alkyl groups. Tertiary carbocation has three alkyl groups which can stabilize the positive charge through hyperconjugation. So it will even be more stable, or the positive charge on carbon will be substantially reduced as compared to the positive charge on the secondary carbocation. So that's why they can easily form. So once they are formed, the next step is where the chloride ion, so there are two electrons on this chloride, which can easily be donated to the positive charge to form a new covalent bond, as you can see, and therefore you synthesize the alkyl chloride. Where is the chloride coming from? It's coming from HCl. Remember, Lucas reagent consists of HCl and zinc chloride. Zinc chloride is just to coordinate the hydroxyl group to make it a better leaving group and also to improve on the electrophilicity of the carbon, which is bearing the positive charge, or the electrophilic carbon. So once that happens, then the reaction can easily proceed and you get the alkyl halide. So depending on the nature of the substrate or the starting alcohol, whether it's primary, secondary, secondary, or tertiary, it can proceed either via SN1 or SN2. For secondary and tertiary alcohols, they always, to form the alkyl halides, they always proceed via the carbocation formation or via SN1 mechanism. But for methyl and primary alcohols, they always proceed via SN2 mechanism to form the corresponding alkyl halides. So when a primary alcohol reacts with Lucas reagent, ionization is not possible. The primary carbocation is too unstable. I've already indicated that. Primary substrates react by SN2 mechanism, which is slower than SN1 reaction of secondary and tertiary substrates. But primary and methyl substrates can only undergo SN2 mechanism to form the corresponding alkyl halides. And it's because, again, we've said the methyl and primary carbocations are not stable. So they can only, the reaction can only proceed via the SN2 mechanism. But for tertiary and secondary alcohols or substrates, they can proceed through the carbocation formation or through ionization to form the corresponding alkyl halides. So for example, when 1-butanol reacts with the Lucas reagent, chloride ion attacks the complex from the backside, displacing the leaving group. So that's how SN2 mechanism is. We will discuss it further. So this is the SN2 mechanism with Lucas reagent, and it's usually slow, and it's only the methyl alcohols or substrates and also the primary alcohols or substrates that can undergo SN2 mechanism, because the mechanism does not proceed via formation of a carbocation. So again, the first step is the same for both tertiary and secondary alkyl, or SN1 and SN2. So the first step is coordination of the hydroxyl group to make it a better leaving group, and also to make the carbon which is bonded to the hydroxyl group a better electrophile. So that step is the same for all the substrates. And then the next, the difference between the SN1 and SN2. For SN1, then this bond could break and form a carbocation. But for this, for SN2, for primary and methyl alcohols, that does not happen. So once this has been formed, it means this carbon is electrophilic enough to react even with the weak nucleophiles like chloride ions. So it's electrophilic, so it will attract the negative charge on chlorine. So the chloride will use the 2 electrons to form a new bond to this carbon, and it will attack or donate electrons from the backside or the other lobe, the smaller lobe of the sp3 hybridized orbital of this carbon. So of course, this carbon is sp3 hybridized, and each of these hybrid orbitals are overlapping again with the hybrid orbitals of the atom that they are forming a covalent bond with. So the reference orbital we are talking about is the one which is forming a bond to the sp3 hybridized orbital of oxygen. So the sp3 hybrid orbitals usually have 2 lobes. One of it is large and another one is small. So the larger lobe is the one which usually overlap with the other hybridized orbital, like for example, in this case, with the sp3 hybrid orbital of oxygen to form this covalent bond. But it has also a smaller lobe which protrudes on the other side. And that is the lobe where the chloride or the nucleophile is going to donate electrons to that lobe and form a covalent bond. So at this stage, of course, this bond is still there. It's not broken completely. So this will be tending to form, this will be tending to break at some point. So the next step is here. This is a transition step, and all these reactions take place at a go. They are concerted reactions. It's a one-step reaction as compared to the SN1, which is a two-step reaction. So this happens at the same time. So this, after the hydroxyl group has been coordinated with the zinc chloride, then of course this becomes a good leaving group, and this carbon bearing the hydroxyl group becomes also more electrophilic. So the nucleophile now reacts, and then the bond will start to form. This will start to break and lead to transition state, which is the high energy state. And it's because now carbon is tending to have 5 covalent bonds. And remember, carbon only should have 4 covalent bonds when it's stable. But when it's tending to have 5 covalent bonds, then it becomes very unstable and with a very high energy level. Then after the transition state, of course, this bond to chlorine will form completely, and the bond to oxygen and this other part of the molecule will break off and form the product. So you have the alkyl chloride and also this other byproduct. So that's how this is the SN1 mechanism, and it's a slower reaction as compared to the SN1. Another way in which you can synthesize alkyl chlorides from alcohols is to use thionyl chloride. So reacting alcohols with thionyl chloride, then it can result to alkyl chlorides. And then you have 2 additional products. You have sulfur dioxide and also hydrochloric acid. But one of the advantages of this reaction is that these 2 are gases, so they easily get evolved from the reaction mixture, and you get the product in high yields. But for this other reaction, these are the products. This is not gaseous, so it will remain in the solution. So when you want this alkyl chloride, you have to purify it further for you to obtain the alkyl chloride. So add an additional process or 2 or 3 additional processes. But for this, since it's gaseous, it will be evolved from the reaction mixture, and then you get only the final product in good yields. And another reason why this is a better way of synthesizing alkyl chlorides is because you will have these gases evolving from solution, so you cannot have them reacting with the product, the major product, to get the reactants. Remember, there's also that usually when you have reactions, there's usually also a reverse reaction towards forming the reactants. So this is not able to happen because already the sulfur dioxide and HCl will be evolved from solution. So thionyl chloride is often the best reagent for converting an alcohol to an alkyl chloride. The gaseous sulfur dioxide and HCl byproducts leave the reaction mixture and ensure that there can be no reverse reaction. Under the proper conditions, the thionyl chloride reacts by an interesting mechanism below. In the first step, the non-bonding electrons of the hydroxyl oxygen atom attack the electrophilic sulfur atom of the thionyl chloride, and a chloride ion is expelled and a proton is lost to give a chlorosulfite ester, which is usually very unstable. In the second step, the chlorosulfite ester ionizes when R, or the substrate, is a secondary or tertiary alcohol. But if it's a primary or methyl alcohol, then there's no ionization that can take place. And we've explained earlier it's because secondary and tertiary carbocations are usually stable as compared to the methyl and primary carbocations. That's why ionization for secondary alcohols and tertiary alcohols can take place, but not for primary and methyl alcohols. And the sulfur atom quickly delivers chloride to the carbocation. So you'll see that mechanism. When R is primary, chloride probably bonds to the carbon at the same time that carbon-oxygen bond is breaking. So that is for primary, they will undergo SN2, where there's no formation of a carbocation. So this is a reaction. You have the alcohol. The first step is just the same as when alcohols were reacting with zinc chloride. And remember, this reaction with the thionyl chloride is to make the hydroxyl group a better leaving group, and also to make the carbon bonded to the oxygen more electrophilic, so that you can easily react with any nucleophile, in this case chloride, which is not very strong. So the two electrons, the lone pair of electrons on oxygen of the hydroxyl group will be donated towards forming a new bond with sulfur. Sulfur always forms 4 covalent bonds just like carbon. So once an additional bond is formed with sulfur, of course, it becomes very unstable. So to get the 4 covalent bonds which sulfur has to form to be stable, then the pi bond, the weakest of the bonds is the pi bond, will break and the 2 electrons will move towards oxygen to form this intermediate. So still sulfur will have 4 covalent bonds. The pi bond, one of the pi bonds has broken, not one of the pi bonds, one of the double bonds, which is a pi bond, has broken and the 2 electrons have moved towards oxygen. Then in the next step again, this forms back the pi bond, and again another bond, to one of the bonds to chlorine has to break for sulfur to have 4 covalent bonds. So it breaks and it leaves with the 2 electrons, so to form the chloride ions. So this chloride ion, this part of the molecule has been stabilized. So S is stable. Now it doesn't have any charge. Oxygen doesn't have any charge. But the oxygen, which was initially the one, the hydroxyl oxygen, still has a positive charge. So it needs to be neutralized. So what will happen is when there's a positive charge, initially remember oxygen was bonded to hydrogen, and oxygen had some partial negative charge, and hydrogen had some partial positive charge. So when hydrogen has some partial positive charge or complete positive charge, we usually term that as acidic. Hydrogen is acidic. So, but now when there's a positive charge on oxygen, the acidity of this hydrogen now increases, meaning the partial positive charge will increase. Then this bond will be highly polarized because there's a positive charge, and the 2 electrons of this covalent bond will tend to move towards stabilizing the positive charge through inductive effect. Then even sometimes the bond can be too polarized that this breaks off, and then the 2 electrons are left behind to neutralize the positive charge, and hydrogen breaks off and leaves as a positive charge. So in this case, you have a chloride ion to facilitate the cleavage of that bond by picking or donating electrons to this hydrogen, which is electrophilic or acidic hydrogen. It forms HCl. And then also the two electrons of this covalent bond move towards stabilizing the positive charge. So you get back the lone pair of electron. Initially, 1 lone pair of electron was used to form a new bond with these sulfur atoms. So you can see here, if you are to account for the lone pair of electrons, you can see 1 is there still. The other one has resulted to the positive charge and this covalent bond. So you have the chlorosulfite and ester, which is an intermediate. So the reaction is still not complete. So depending on the substrate, and we said if it's the alcohol is a secondary and tertiary alcohol, then what happens? The second step is where this bond cleaves. This has now become a very good leaving group. So this can easily cleave. So it cleaves and the 2 electrons of this covalent bond will move towards oxygen. You can see here. So the oxygen becomes negatively charged. So this is what the 2 electrons are the ones which were bonded to sulfur through a pi bond, but now they are up there. And then once this bond breaks, of course, the 2 electrons, even the one carbon was donating to form this covalent bond has moved to oxygen. So carbon will be positively charged. It results into a carbocation, and that is only when the substrate is secondary or tertiary. So the next step now is where this negative charge will be used to form again, to reform the pi bond. And sulfur, remember, only forms 4 covalent bonds, not 5. So immediately this sulfur will have 5 covalent bonds. So again, the weakest bond in this case is going to break, the bond between sulfur and chlorine with the 2 electrons. So this is what it means by delivering the chloride to the carbocation. So once this forms a bond to sulfur, it results to sulfur dioxide. So sulfur becomes complete. Then also this bond breaks. So by forming the bond to sulfur, it delivers the chloride or the chlorine with the 2 electrons of this covalent bond to the carbocation. Then it forms the alkyl chloride. So you have the alkyl chloride and you have HCl, which is gaseous. You also have sulfur dioxide, which is gaseous. So the only major product in the reaction mixture is the alkyl chloride. So this mechanism resembles the SN1, except that the nucleophile is delivered to the carbocation by the leaving group. So SN1, of course, that doesn't happen. Usually the nucleophile is not delivered to the carbocation. But in this case, it's a bit different, deviates a bit from SN1, but other properties of SN1 are the ones which this reaction entails. So here, but this particular one, the nucleophile is delivered to the carbocation by the leaving group, giving retention of configuration. So another new, one of the properties of this particular reaction is where there is retention of configuration from the substrate to the product. The retention, the two, there is retention of configuration of the two, as shown in the following example. But under different conditions, retention of configuration may not be observed. So it's not always the case. So for this particular example, you start with the 2-octanol, R2 octanol. Of course, this carbon is chiral attached to 4 different groups. That's when you can easily give it a configuration. So here it's R configured. It's 2-octanol, but the orientation is R. Then reacted with thionyl chloride in this solvent, dioxane. This is not taking part on the reaction, but just dissolving the reactants. So the product is also R. The configuration is the same. So you can see it's the same, the hydroxyl group and also the chloride. So it's the same. So it will still, the product will be R2 chlorooctane, and the yield you can see is 84%. But if it was an SN1, SN1 mechanism, usually it leads to a mixture where you have retention of configuration and also inversion of configuration. Then lastly, we can also synthesize alkyl halides, different alkyl halides, as you'll see, from a reaction of alcohols with phosphorus halides. So several phosphorus halides are useful for converting alcohols to alkyl halides. And phosphorus tribromide, phosphorus trichloride, and phosphorus pentachloride work well and are commercially available. So this is a way to synthesize those alkyl halides. We've talked about the alkyl chlorides and alkyl bromide, but you'll see later also an example of how you can synthesize alkyl iodide using phosphorus halides. So if you start with 3 moles of alcohol, react with phosphorus trichloride, you'll be able to get 3 moles of alkyl chloride. If you start with 3 moles of alcohol, react with phosphorus tribromide, you get 3 moles of alkyl bromide and other byproducts. Then if you start with 1 mole of alcohol, react with 1 mole of phosphorus pentachloride, you'll get 1 mole of alkyl chloride with other byproducts. So phosphorus halides produce good yields of primary and secondary alkyl halides, but none works well with tertiary alkyl halides. So this is a better way in which you can easily synthesize primary and secondary alkyl halides, but not tertiary alkyl halides, because the way the mechanism is, it's through SN2 and not SN1. So the 2 phosphorus halides used most are phosphorus tribromide and phosphorus iodide combination, which generate usually phosphorus triiodide. So phosphorus tribromide is often the best reagent for converting a primary or secondary alcohol to the alkyl bromide, especially if the alcohol might rearrange in strong acid. Rearrangements usually take place when you have SN. The possibility of rearrangements is usually through formation of carbocations in SN1 reactions. But SN2, there's no rearrangements that can be observed. So a phosphorus and iodide combination is one of the best reagents for converting a primary or secondary alcohol to the alkyl iodide. For the synthesis of alkyl chlorides, thionyl chlorides generally gives better yields than phosphorus trichloride or phosphorus pentachloride, especially with tertiary alcohols. So if you want to synthesize alkyl chlorides, the best method is to react alcohols with thionyl chloride and not any other method. So the following are examples of conversion of primary and secondary alcohols to bromides and iodide by treatment with phosphorus tribromide and phosphorus iodide combination. So here, this is a primary alcohol. You can see this carbon, which is bearing the hydroxyl group, is attached to one other carbon. But if you look at the carbon it's attached to 3 other carbons. So this carbon is a tertiary carbon, but it's not even tertiary, it's quaternary. It's attached to 1, 2, 3, 4 carbons, but somebody might confuse this because of this bulky nature of this group, which is attached to the carbon bearing the hydroxyl group, and they can easily classify this alcohol as a tertiary or any other class, place it under any other class. But you look at the reference point is that carbon which is bearing the hydroxyl group. How many other carbons is it attached to? In this case, this is attached to 1 or bonded to 1 other carbon. So this is a primary alcohol. If it's attached to 2 other carbons or bonded to 2 other carbons, it will be secondary alcohol. If it's attached to 3 other carbons or bonded to 3 other carbons, then it will be known as a tertiary alcohol. So this is a primary alcohol, and we've said usually primary and secondary alcohols react very well with phosphorus halides to form the corresponding alkyl halides through mainly SN2 mechanism. So there's no formation of a carbocation in that mechanism, and there's no rearrangement. When you hear carbocation formation at any step, then the possibility of rearrangement is there. But if there's no carbocation formation, like in SN2 mechanisms, there's no rearrangement that is possible. So this primary alcohol can react with phosphorus tribromide to form the corresponding primary alkyl bromide. So again, the yield is not so low. It's good enough. So this is another primary alcohol. This carbon, which is bearing the hydroxyl group, is attached to 1 other carbon. Okay, it's CH214. It just means that they are CH14 CH2s, which are attached. So the total number of CH2s are 14, but this carbon is attached to 1 other carbon, reacting with a mixture of phosphorus and iodide to generate phosphorus triiodide. Then the final product is going to be this alkyl iodide, and the yields you can see is also good, 85%. So the mechanism of reaction with phosphorus trihalides, the mechanism of reaction of alcohols with phosphorus trihalides explains why rearrangements are uncommon and why phosphorus halides work poorly with tertiary alcohols. The mechanism is shown here using phosphorus tribromide as the reagent and also phosphorus trichloride and phosphorus triiodide, which is generated from a combination of phosphorus and iodide or iodine, which reacts also in a similar manner. So this is one of the reaction of alcohols with phosphorus tribromide. You note here that this is a neutral molecule, and this neutral molecule phosphorus is bonded to 3 bromine atoms. So it's forming 3 covalent bonds. So again, the first step is similar to the ones we've just discussed, where hydroxyl group, since it's a poor leaving group, it coordinates with this phosphorus and forms a complex, which now where the hydroxyl group has been converted to a beta leaving group, and also the electrophilic carbon, which is bonded to oxygen of the hydroxyl group, has also been made a beta electrophile. So the lone pair of electron is used to form a bond with this electrophilic atom, that's phosphorus. So there's that covalent bond. And then there'll be a positive charge because of oxygen using a lone pair of electrons. So this is the other lone pair of electron, which has been used to form this covalent bond. And immediately that happens, it means that phosphorus, if we don't, there'll be no bond breaking from phosphorus, it means it will have 4 covalent bonds, which will be very unstable. So one of the bonds to bromine has to break and leave with the 2 electrons. So to form a bromide ion. This bromide ion is a nucleophile, and it's the one which is going to be used to bond with electrophilic carbon. So the next step here is where now through SN2 mechanism, the bromide, which is a nucleophile, will attack the carbon, which is the electrophilic carbon from the backside, I've already explained. And then immediately it forms the pentavalent not intermediate transition state, which is very unstable, and it's a high energy state. Then finally, this breaks off and it forms this leaving group and also an alkyl bromide. So there's no step here where you have carbon bearing a positive charge. And don't get confused with this positive charge on oxygen. We have talked about carbocation formation. So SN2 does not proceed through the formation of a carbocation, not any positive charge. You can see this and think that this is a carbocation. This is not. It's a positive charge on oxygen, which results because of the covalent bond, which is going to be formed from the hydroxyl group to the phosphorus atom. So no rearrangements are common because no carbocation is involved in the reaction. So for these reactions, there's no carbocation formation as we've seen in SN1 reactions. It also explains the poor yields with tertiary alcohols. It can happen, but the yields are very low and they will not be very important. So this is it's not the best way to synthesize tertiary alkyl halides. This final step is an SN2 displacement where the bromide attacks the backside of the alkyl group. And this attack is hindered by the alkyl group if the alkyl group is tertiary, and therefore the most suitable substrates are methyl, primary and secondary alcohols towards the synthesis of methyl, primary and secondary alkyl halides, mainly bromides and iodides. In the case of tertiary alcohol, an ionization to a carbocation is usually needed, as we've seen in SN1 reactions. Such an ionization is usually slow and invites side reactions. That's why you see that these reactions do not favor mainly the tertiary alcohols as substrates, only the primary and methyl alcohols to form the methyl and also primary alkyl halides. So this is a summary on how to synthesize alkyl halides used from alcohols. So if you want to synthesize a primary or secondary alkyl chloride from primary or secondary alcohols, then you use thionyl chloride in both cases. But if you want to synthesize tertiary alkyl chloride from a tertiary alcohol, you use Lucas reagent, which is a mixture of zinc chloride plus HCl. If you want to synthesize both primary and secondary alkyl bromide from primary and secondary alcohols, then you use phosphorus tribromide or HCl for primary alkyl bromides, but for secondary you use phosphorus tribromide and tertiary, you use hydrobromic acid. If you want to synthesize alkyl iodide from, for example, primary and secondary, from primary and secondary alcohols, you use a mixture of phosphorus and iodine, or in the two cases. But if you want to synthesize a tertiary alkyl iodide, then from, of course, as a tertiary alcohol, then you use hydrogen iodide acid. So we'll stop there. Next time we will be discussing on the reactions of alkyl halides, that is nucleophilic substitution and also elimination reactions. Thank you.